Yeah, okay, so welcome back, everyone. So today it's my pleasure to welcome Tobias Schröder. We'll be talking about energy discrepancies, training of energy-based models without Schröder or MCMC. Yeah, thank you.
Thank you very much for having me. I'm very happy to present our work. So this is joint work with Zijing, Jenning Lim, Ingjen Li, Sebastian Vollmer, and Andrew Duncan on how to train energy-based models. And just for context, we don't know how to put the presentation full screen. So I'm going through the keynote like this, and let's see how it looks like. So I just want to briefly explain why we are interested in energy-based models and what they are. So energy-based models are an example of a probabilistic generative model where we take data and we assume that it is actually explained as IID samples from some underlying unknown data generating distribution. And so we try to approximate that data generating distribution using some neural network probabilistic model. And examples of these types of generative models that are quite famous are diffusion models or variational autoencoders. And there's also normalizing flows. And so diffusion models are actually what's behind AI generated images. So as you can see, this very basic concept of estimating the data generating density is extremely useful to generate high quality images if you put a lot of engineering into that process. So what we do is so-called energy-based modeling, which is another candidate of generative probabilistic models. The background lies in physics, where the so-called Boltzmann distribution describes the probability density of a statistical physical system at a fixed temperature that has a certain energy U. And an example of that Boltzmann distribution that might be intuitive to you is the barometric height formula. So at fixed temperature, the density of air decreases exponentially with altitude. So that's why if you hike up a mountain, the air gets thinner and thinner. So the idea of energy-based models is that we treat data like these physical particles, and we try to learn the energy landscapes such that our data density is described by that Boltzmann distribution. So how does this look like? We take our data, which is just given as some points in usually a Euclidean space. And then we try to fit the probability density p theta, which is given as the exponential of a so-called energy function. And that energy function is modeled using a neural network. And this is a very interesting approach because that neural network can be chosen with an arbitrary architecture that is suitable for your type of data. So for example, if your data are images, you might be interested in convolutional neural networks. For a graph, you might be using graph neural networks, or for some time series, you might be using an autoregressive model. So you can tune your energy according to the data. You might even be able to use some physical knowledge if there's an actual physical energy at work. The reason why this is not so easy to do in practice is because this exponential of the energy function only yields an unnormalized distribution. And the normalization of that distribution depends on all the neural network parameters. So if you want to optimize this distribution using maximum likelihood estimation or a different type of distance between probability distributions, you will find very quickly that that normalization needs to be included in your optimization and makes a lot of trouble. So since diffusion models are so successful, I quickly want to highlight why they are not the only generative model you should be interested in. Because these different types of models have different qualities. So diffusion models really learn how to sample from the data distribution, but they don't give you information about the data density explicitly. So if you're interested in like high quality images that are AI generated, then a diffusion model will work well. But if you're interested in learning some underlying features in your data set, like some representations, then a variational autoencoder is more suitable. And we are interested in inference downstream tasks. So we want to infer something about our data from the generating process. And in that case, the density information is very useful, which motivates why energy-based models or normalizing flows are interesting. And energy-based models are more flexible in the architecture than these normalizing flows, if you're familiar with them. So to give an example of how this density information can be used, imagine that you have some noisy simulator called G, which depends on some parameters. You can imagine that this simulator belongs to a dynamical system, say a noisy Lotka-Volterra system. And so you don't have any likelihood for that simulator, but you are making observations and you would like to infer what's the parameter that explains these observations. That's called simulation-based inference. And an energy-based approach to do simulation-based inference is that we can simulate our system for many, many choices of parameters and then learn the joint distribution of the observations we are making with these parameters. And an energy-based model is very flexible to do this, and we can subsequently use it to make inferences over our parameters given observations that we see in practice. So on the right here, you see a system of neurons firing, and what we want to infer is the synaptic strength between these neurons. And the energy-based approach works quite well for this inference. So this is a work by Glaser, not by our group. Something related that is also interesting is you have labeled data like images together with the class label. Then you can also learn the joint distribution of these images together with their labels. And then you can use that model as a classifier. You can also train it as a classifier, but it will give you, together with the prediction of the label, also some likelihood information that the input that you're giving the classifier is not out of distribution. So you can check that your classifier is well calibrated and detects any kind of out of distribution inputs that should not be classified. Finally, in a medical imaging context, a common problem is that you are making, say, medical scans and you only know a noisy forward operator similar to the simulation-based context. And the way you usually recover the true image that you see in a medical scan is using some maximum a posteriori estimate. And what you find mathematically is that this estimate will depend on the maxima of the log likelihood of the data generating distribution. So usually this term is replaced with some regularizer, like a total variation. But what you can also do is learn offline and such an energy function that is associated to the data. And then your maximum a posteriori problem becomes the minimization of, for example, here this mean square loss plus a minimization of the energy function. So you want to recover high likelihood samples from your noisy observation. And there's many more applications of these models, like concept learning for robotics, anomaly detection, and so on. So this is a slide of references if you're interested in learning more about this topic on how to apply it. So if these models are so useful, why are they not more common? Actually, I would say they are pretty rare. Well, training these energy-based models is extremely difficult. The standard approach is called contrastive divergence. It's basically the only approach that is used in practice, to my knowledge. And what you try to do is to basically do maximum likelihood estimation. And the maximum likelihood, the gradient of that log likelihood function then becomes the gradient of the energy, but also another term, which is the expectation of the gradient of the energy according to that energy-based model itself. And so to approximate this log likelihood gradient, we need to employ Markov chain Monte Carlo methods. For example, we need to run a Langevin sampling scheme starting at the data sample. So the sampler will essentially hallucinate states that have high likelihood according to your current energy-based model. And those will be treated as negative samples that need to be where the energy needs to be adjusted so that the energy of data points is basically pulled down, and then the energy of these hallucinated states is pulled up. And since the Monte Carlo sampling would take a long time to converge, you actually truncate that sampler after a small number of steps, in practice usually less than 10 steps. And what happens is that the estimates of the energy function are quite malformed, so they are a little bit blurry and usually don't produce accurate estimates of the data density. So in the inference context that I outlined before, that's suboptimal because we would like to learn a more accurate representation of our data density. To give some context why that bias appears. So since we are truncating that MCMC chain, we don't perform maximum likelihood estimation anymore. What we do instead is actually minimize a different objective called, this contrastive divergence objective, which is the difference of two Kublai-Leibler divergences. And this, in the second term, this Q theta K represents K steps of our Markov chain that targets our model P theta. And if we take the gradient of this objective, we see that the first two terms correspond exactly to the contrastive divergence update. So that's the update that we use for our neural network. But there's an additional entropy term, which we don't usually include in the contrastive divergence update. And it was argued in the original paper by Geoffrey Hinton that that term is negligible. Later it was argued by Satskava and Thielemann that actually that's a problem. It leads to biased estimates. And finally, there were some attempts by Yilun Du and co-authors to treat that term by estimating that entropy. But in the end, it still holds that basically the typical contrastive divergence update that is used in practice is not the gradient of any loss function, which means that we don't have theoretical guarantees for its convergence. And in practice, the states that we observe when the algorithm converges are not accurate. So a different type of objective that you might be familiar with is called score matching. So in score matching, we use the idea that if we take the gradient of our log density, the gradient of our intractable normalization of the model will be 0, which means that these Stein scores, so the gradient of the log density, is independent of that intractable normalization. And so if we compare the Euclidean distance between the score function of our data density and the score function of our model, that objective is independent of that intractable term. And via an integration of parts, you obtain a loss function that you can approximate in practice. And the problem with this approach is that these scores tend to be nearsighted. So if you take two bimodal Gaussians, and like you see in the right in figure A, and the only thing you change between these two bimodal Gaussians are the mixture weight the mixture weights. So in one distribution, the mass is more in the right mode, and in the other distribution, the weight is more in the left mode. Then the scores of these two distributions looks almost identical. And the score matching loss will be close to zero, and it will be very difficult to infer the mixture weight accurately. So that's why we call these score matching losses nearsighted. So our work essentially tries to resolve both these issues. So the issue that contrastive divergence is biased and doesn't have accurate estimates, and score matching is nearsighted. And we call this approach energy discrepancy. So from the perspective of contrastive divergence, let's look again at the loss function that we are basically trying to approximate. We have this difference of two Kullberg-Leibler divergences. And the issue that we are facing is that the transition density of our Markov chain, so the Markov chain itself, the sampler, depends on the parameters of our energy-based model. And this means that when we take the gradient of this objective, we get this really difficult to estimate entropy term that is always neglected in practice. Can we somehow do this kind of transition operator without the dependence on the parameter? And it turns out you can. You can just define a very general perturbation operator Q, which is the convolution of our density with some conditional density that we call a perturbation. And then one thing we need to change about the contrastive divergence objective is that we need to apply this operator not just in the first argument of the KL, but in both arguments. But if we do that, then the difference of these two Kullberg-Leibler divergences is again a statistical divergence. So it is non-negative, and if it's zero, then we know that p data equals p theta. And if we expand all the terms, what we find is that there's only two terms that depend on this neural network that we are trying to learn. The first one is the same as in contrastive divergence, so it's the expectation of our energy function over the data distribution. And the second term, the contrastive term, is basically the perturbed energy function that the expected value of the perturbed energy function with respect to perturbed data points. To maybe come from the other side, or from score matching, the idea is as following. So what we're trying to do is we are trying to fix the blindness of score matching. And one thing you can do to make score matching more aware of the mixture weights is you put noise on your data and you put noise on your model. And then this noise will yield a larger overlap between these distributions, and that overlap can be used by score matching to identify these mixture weights that it's usually blind to. So that idea is actually used, it's basically annealing, and that idea is used in score-based diffusion models as well. And now what we can do is we can take that score matching objective between these noisy data distributions and the noisy model, and we can say, okay, now this new noisy objective is more aware of the mode distributions, but it will be less accurate because we are basically trying to estimate a noisy data density. So we integrate over just all these noise levels that we introduce. And what we find is, again, the difference of two energy expectations. So first, the expectation of the energy function with respect to the data distribution, and the contrastive term, which is the energy associated with your perturbed model, and we take the expectation with respect to the perturbed data distribution. So as you can see, we can relax contrastive divergence using that perturbation operator and obtain this difference of two energy expectations. Or we can try to fix the blindness of score matching by introducing a perturbation which somehow gives score matching more awareness of its surroundings. And in both cases, we find the same objective, the difference of two energy expectations. And we call that the energy discrepancy. So to introduce it formally, we take an energy-based distribution. So that's the Boltzmann distribution. Probability is proportional to exponential of minus the energy function. We define, the user defines this noising distribution, this perturbation, and then associated to our model and this perturbation, we introduce the so-called contrastive potential, which is basically the energy function associated to the energy-based model convolved with the perturbation. And then we define energy discrepancy like this. So the expectation of the energy with respect to the data minus the expectation of the contrastive potential with respect to the perturbed data. So this energy discrepancy objective is equivalent to minimizing this difference of two Kullback-Leibler divergences, which, as I said, is a statistical divergence. So what we're doing is fine from a theory point of view. And in fact, what we prove is that if you use variational derivatives, functional derivatives of this objective, you find that energy discrepancy is functionally convex in the energy function and has up to like the additive constant that you cannot resolve, this normalization constant, a unique global minimizer at an energy-based model which is proportional to the data density. Oh, and I should emphasize that this objective by construction does not depend on a normalization constant. Since when we take these two KL terms, the normalization constant cancels out between the two terms. So now that we define this objective, you might be wondering what perturbative process should I use in order to get a good energy discrepancy objective. And so what we studied is the limiting behavior if we choose a perturbation that is associated with a diffusion process. So for a diffusion process, which is here defined by a stochastic differential equation with a drift term A and a diffusion coefficient B, you find that energy discrepancy can always be expressed as an integral over time of basically a diffusion score matching discrepancy. So in the special case where our diffusion process is a Brownian motion, this inner term in the time integral becomes a standard score matching objective. And so what you can basically say is that energy discrepancy generalizes score matching and considers the score matching objective at these various noise scales that are introduced by the diffusion process. The way you should interpret this diffusion coefficient B here is that it basically prefers certain directions in space which get a higher value. So it basically slices certain directions in space that we put more noise to. And so we get a slightly different objective in that direction. Yeah. I think the more interesting relationship you get is when you now take this time parameter to infinity. Because in the case when our drift term is, sorry, that's actually not quite right. So in the case when our diffusion term is just an identity. So we just have a Brownian diffusion. We can show that this energy discrepancy converges to maximum likelihood estimation as you increase time to infinity. One moment. So considering the question, what perturbation should we choose for this objective? If you just choose a standard Gaussian perturbation that has variance t, so that's the transition density associated with Brownian motion, then you find that energy discrepancy based on this perturbation function converges to maximum likelihood estimation at a linear rate in this time parameter t, as measured by the Wasserstein distance between the data distribution and the energy-based model. So as long as we can approximate this objective function with the low variance, we actually don't lose much compared to maximum likelihood estimation without requiring this Markov chain Monte Carlo step that you need in contrastive divergence. To illustrate this point, let's come back to the example where you have a Gaussian mixture, you have a bimodal Gaussian mixture, and you don't know the mixture weight. So you try to estimate which of the modes has more weight. In this case, the true weight is 0.2. So 20% of the mass is in one mode and 80% is in the other. If you use the maximum likelihood loss, you find that it's a really sharp quadratic with a clear minimum at 0.2. While for score matching, as I said, it's basically blind to the mixture weight. So it's just a zero constant function. While for energy discrepancy, you find that it's also convex around this minimum 0.2. And as you increase the noise scale, the curvature increases around that minimum, and it becomes easier and easier to estimate the true mixture weight with low variance. And you observe that in the mean square error, when you actually estimate that mixture weight, how as you increase this time parameter from 1 to 10, on a log-log plot, the variance or the mean square error of your estimate decreases linearly. So how do we use this objective in practice? Well, you somehow need to estimate it from samples. So this is kind of a schematic how you would do that. You take your data points, you apply the forward perturbation, and then you need to estimate this contrastive potential term, the minus log integral exponential of energy times the perturbation operator. And you can do that basically by just computing the inverse of your forward perturbation, as I show here. Since the normalization of your forward operation is independent of the neural network parameters, so it just becomes irrelevant for your optimization. And that way you obtain negative samples, and then you compare the energy of your data samples with the energy of these negative samples as measured, and you apply a log sum exp operation to them. So to kind of make that a bit more clear in the Gaussian case, which is the one that we use in practice, we take our data samples. Now we want to approximate these outer expectations. So we can do that by applying noise to our data. And we do that just once. So we just use, for each data point, we just initialize one random Gaussian to obtain a perturbed sample. Oh, something happened here. And then we need to condition on that perturbed sample to approximate the contrastive potential. And the nice thing is that the Gaussian transition density is symmetric, so we can just flip the two arguments, condition on the perturbed sample, and apply another Gaussian perturbation to obtain this contrastive sample. And we do that m times in practice to obtain a loss function that we can then very easily implement and stably approximate and optimize. And we found that this works really well in many two-dimensional data sets, where we typically chose this m, so the number of samples, contrastive samples that you, like negative samples that you need to sample for each data point, if we chose that like 200 or 500. But what we wanted is to make this more scalable to high dimensions, and to like lower samples m that we use. Oh, sorry, I have some slides that I removed. So, okay. And if you increase the variance of your perturbation, or if you decrease the number of contrastive samples that you use in your sample approximation of the loss, what you find is that your loss suddenly starts to diverge to minus infinity. And it was very mysterious why that happens. But actually the explanation is quite simple. And I think it might appear in other cases where you take the logarithm of a sample approximation. In theory, what we are doing is well justified and there should be no issue. But imagine that we have an energy-based model which is basically constant, and then we come to the edge of our data support, and at the edge of our data support, the energy increases towards infinity, which means that our density decays exponentially. So that's actually what we want, because of course we want that our density goes to zero when we reach the edge of our empirical data support. And if we convolve that energy with our Gaussian perturbation, that remains bounded in theory. But what happens in practice is that it doesn't remain bounded, because whenever we have a random sample xi, and xi is positive, then, and we use our sample approximation based on xi, so we estimate that integral with just a single sample, then this contrastive potential that we estimate with the sample is just the decay rate of our density times the value of that sample, and that goes to infinity if this decay rate b goes to infinity, which means that the optimizer in your machine learning pipeline can notice that if it just increases these like the decay of the density at the edges of the data support to infinity, then the optimization can basically completely disregard any kind of learning from your data, and it can just drive this energy to infinity to also minimize the loss function that we're using to minus infinity. So that's why we introduce a very simple fix for that. You just offset the logarithm by some value w, and this value w introduces kind of a margin between your data samples and between the energy of the data samples and the energy of your contrastive samples. And it prevents that this margin between these two energy values can just grow indefinitely. So if that margin grows above w, that value will basically be exponentially dampened compared to all the other terms. So in the previous example, for example, whenever xi is positive, it will kind of be disregarded, and you only consider contributions of negative random samples into your optimization. And to illustrate, so in this case, we just have Gaussian data, 1D Gaussian data. Empirically, the data support ends. Of course, you know that in theory, the Gaussian has infinite support, but in practice, your empirical data support ends somewhere. In this case, at like 1.7 or so. And if we don't use this W stabilization, then it can happen that the neural network learns essentially a potential well, so the energy is zero, where it sees data, and then at the edges of your empirical data support, it just goes to infinity very quickly. While if you introduce this W stabilization, you will of course bias your estimate a little bit. So that is a hyperparameter that you need to tune, but you get a quite good fit to the ground truth, which is a square potential. And in fact, our experimental results confirm that this is a good approach. So what we use when we estimate 2D densities is just a W value of 1, and we just use 4 samples for each data point, which is extremely computationally cheap compared to score matching or contrastive divergence. And as you can see, we learn these energy functions much more quickly than these other approaches. And compared to contrastive divergence, we have some theoretical guarantees, which is really nice. So for example, you can see for this data set that contrastive divergence has these kind of blurry estimates of the energy, while with this energy discrepancy approach, since it has better theoretical guarantees, the support is estimated really accurately. And in this example on the bottom of the page, the data is a mixture of 25 Gaussians, and score matching gets the Gaussians right, but doesn't know the relative weights, while our approach gets these mixture weights very accurately, that they are all uniform. So that's very useful to employ this approach in downstream tasks, where you want to be sure that what you're estimating is right. Since we are in the generative modeling world, we also need to demonstrate some examples on images. And actually, there's a curse of dimensionality there, which is not the typical one. So the curse of dimensionality for this approach is that in high dimensions, random vectors become orthogonal with very high probability. And that means that a random noise direction in high dimensions is basically completely uninformative for how the data distribution looks like. And what's more is that basically high dimensional data typically lies on a very constrained support or manifold. So that's a so-called manifold hypothesis. And that means that actually the log density is not well defined. So in most places of your high dimensional space, the density is 0 and the log density should be infinity. So in order to kind of solve this problem, we use so-called latent energy-based models, where you take a probabilistic model that has a similar form of a variational autoencoder. So you have some latent codes which are distributed according to the energy-based model that you're learning. And you have a Gaussian decoder, which is the same as in a variational autoencoder. Then for each data point, you can sample the latent code by basically just sampling from this joint distribution under the integral sign. And then update the parameters of the decoder network by minimizing the reconstruction error of the data point, and updating the parameters of your neural network by minimizing one approach to learn energy-based models in latent space. So we, of course, do that with energy discrepancy, but you can also do that with the other approaches like contrastive divergence or score matching. And that actually gives us really good results on images compared to other VAE or energy-based approaches. So we get kind of higher quality images as measured by this FID score compared to score matching and contrastive divergence, and relatively accurate colors. So I'm quite happy with these results, although I still consider them preliminary. And I know that you're probably not so interested in images, so you should really just consider this as a benchmark of how this performs in high dimensions. So you can do something similar for other types of data, like maybe something that you find from a dynamical system. Before I finish, I quickly want to introduce somehow what else you can do with this beyond the Euclidean domain. Because since we are not using gradients or standard MCMC schemes, you can apply this very easily in, say, on discrete data by just defining a perturbation operator that works well in this discrete domain. For example, here for binary MNIST, where your data takes values in a binary space to the dth dimension, you can think of a perturbation which basically pools the pixels in your image, and the contrastive sample is obtained by unpooling. Similarly, similar to the Gaussian noise, you can also, for example, apply Bernoulli noise. So you sample a Bernoulli mask where you flip the values of your data vector. And in both these cases, we again get an energy discrepancy that you can use to learn an energy-based model. And the results are really confirming of this approach. So on the left, you see the two-dimensional data sets that I showed before, but they are discretized by computing so-called gray codes. So that's considered to be already a relatively hard problem for discrete energy-based models. And we observe really no problem for energy discrepancy to learn these densities. Again, on images, it's a bit more tricky, but at least in the discrete domain, we can actually estimate, like get good samples without any latent variable models. So remember before we needed this variational autoencoder kind of approach. On discrete spaces, we can actually go with just our loss function. And again, we hope to improve these results with future work. So thank you very much. I hope you took something away from this. And thank you for the invitation. And I'm very happy about any questions that you might have.
Yeah,
Let me just get something for my throat.
Yeah, thank you. Itamar, did you want to ask a question? Or?
Yeah, do you hear me?
Yeah, we can hear you. Yeah.
Yeah.
Go ahead.
Okay, since you mentioned discrepancy, there is a fellow by the name Niederreiter who did dimension reduction via discrepancy sets. And because, and this is in the context of quasi Monte Carlo, which is not so remotely connected to MCMC. So it could be that some of the challenges that you have shown, and of course, the big advantages of energy discrepancy may be solved by that approach. The other question I have is about entropy, relative entropy, and Fisher information. And indirectly, you use them in KL and in the other expressions, but these things are also connected.
Yeah. So for the first point, so you said discrepancy and dimensionality reduction in quasi Monte Carlo. Is that just so yeah, I need to find that reference. You remember what the author
The
was
reference
name?
is neither writer. It's a long name,
Okay.
and I probably pronounce it wrongly, but you will find it because he made many papers about it.
Okay, I will have a look at this if it. Thank you very much.
And also somebody in Canada by the name Ecuyer, ECUIR, something like that, also specializing in quasi Monte Carlo.
Thank you. I will look for that. So for your question about Fisher divergence and Kuiper-Gleiber divergence, which is very, yeah. So I showed, let me find this.
I think you have used it indirectly, so,
yeah,
but you didn't mention
exactly.
that explicitly. That's why I just make a note here that these things could be connected, that's all. It's not a deep statement.
They are exactly connected, so.
Here you are, yeah.
Yeah,
Beautiful.
so the Fisher divergence is basically like the time derivative of the KL divergence along some diffusion. And so what this is basically, let me find what's the best. Maybe let's show this one. So the score matching is equivalent to Fisher divergence. So there's just some integration by parts going on.
And probably the relative entropy is also part of
and the right-hand side is basically relative entropy subtracted from each other. So the way you can see this is as the fundamental theorem of calculus essentially happening here, where this is the derivative of the right-hand side. So if we integrate in time, we just get the endpoints of the stem function of score matching.
I
so
see.
if we put
Beautiful.
the Fisher divergence here, we get the relative entropy minus the other relative entropy.
Okay, it's nice to see that it's actually a small world.
Yeah.
Okay, thank you so much for a beautiful talk, physics oriented. I enjoy it very much.
You're welcome. Thank you very much.
Thank you. Other questions or comments? All right, okay, yeah, thank you again, Tobias, very much for the talk. And
thank you very much for having me.
Yeah, thanks everyone. Bye-bye.
Thank you. See you around.